Welcome. In this session, we'll explore a convex problem that has two linear inequality constraints. Our objective function will be, we'll take the first entry of the argument, square it, and then add 4 times the square of the second argument. Let's take a look at what two linear inequalities would do when subject to this constraint. Here, what we'll do is we'll consider two constraints. One is that the second entry of the argument vector is less than or equal to 2, and the other is the difference between the second and the first entry are less than to equal to minus 5. Let's graph these. The graph of the first one is saying that its feasible set, or its level set, is this shaded region. So those are all the vectors that have a second entry that's less than or equal to minus 2. When we look at the second constraint, we see that the constraint line, that is the boundary or the level curve of that constraint, is a tilted line, and we can see that the shaded region is the feasible set. So when we say both constraints must be met, what we're saying is that a feasible point has to be inside this region. So inside the intersection of two convex sets, which is a convex set, and in this case, these go to minus infinity here and to plus infinity here. And although it's a closed set, it doesn't have a simple boundary the way that other examples might have. So a feasible point has to be inside this shaded boundary. Now let's take a look at the contours of our objective function. So here are the contours that correspond to this function. And now what we want to do is we want to find a feasible point that has the smallest level possible. And graphically, what that would be is here are our contours, and here is our feasible set. And so we want to know what point is inside this feasible set and has the lowest contour. And we can see graphically that as we get closer and closer to the corner of this feasible set, the contours are getting smaller. And indeed, when we do the computation, that little red dot is the solution to the constrained problem. So in this case, the solution is when both inequalities are equal to. So what we would say is the optimal point, the minimizer, is on the boundary of each constraint and is on the boundary of the feasible set. Now, let's make a small change to this problem. Suppose that we keep the first constraint, and now we change the second constraint to be 2 times the second entry minus the first entry is less than or equal to minus 5. The picture for the first constraint stays the same. The picture for the second constraint is changed. Now this has a different tilt to it. And the intersection has approximately the same appearance, but is numerically a little bit different. And we still have this requirement that a feasible point is inside the intersection, so this is called the feasible set. Now, let's take this objective function and solve this problem again. So here what we see is that now the solution, this minimizer, has two curious properties. One is it's on the boundary of the first constraint, and the other is that if we extend it like this, it's in the interior of the second. So in the first example, the solution to the constrained optimization problem was on the boundary of the feasible set and happened to be on the boundary of the individual constraints. Now we're seeing that it's possible for it to be on the boundary of one constraint and be an interior point of the other constraint. So we can see immediately that linear inequalities are much more complicated to handle than linear equalities were.